I'd like to talk about some blending and filleting work and how an angle between a tangent line and another tangent line can affect the continuity along this boundary. Okay, so this is a case where we have an acute, which is an angle less than 90, or obtuse, an angle more than 90, intersection of tangent lines. And this happens a lot, and the solution for it is adjusting the flow of the center and the flow of the boundaries, and I'll explain why. So here we have a pretty simple problem. We needed a curvature continuous blend with a minimum radius of 2.0. So we simply selected the boundaries or walls and created a curvature continuous radius-based surface with a minimum center radius of 2. And if we turn on our curvature combs, 2. Okay. So this could be fine. Let's check our continuity. So we're asking for curvature. So we'll check our curvature here and on these edges, and it all seems fine. But when we check the interior, you can see that we have a slight issue, maybe a little more than slight. We've got an angle issue, and we've got a curvature issue. Now, why is that? Well, first thing many people, and I would first try and fix that by saying, well, the edges for sure, they want to be edge aligned so that they go all the way to the ends. That does a couple things for us. One, just by the mathematics, it simplifies this surface and gives us a Bezier surface. But it does not fix our internal continuity issue. Okay? So if we look down this fillet, I'd like you to take note of the shape of the control vertices. And I'm just going to delete this locator. I'd like you to look at these control vertices and see how they're quite uniform. Okay? They just easily go across. Now, another solution that a person might have, or even based on my first statement of acute and obtuse angles, you might say, well, let's get rid of this angle situation in here by making this internal edge aligned. And then we could ask for explicit control, and then we could ask for Bezier. We could go through a whole bunch of things, but in the end, what I'd like you to look at is just at this point right here, let's look at this surface's shape. Because we know this was a flat surface intersected with this fairly simple surface, but look at what edge align and the interior does to the shape of this tangent. We go back to free, we get a nice clean line. We get a clean tangent and a clean curvature. Okay, so I think this is what we need to have. All right, or start with. Next, I'd like to point out just how control vertices look and how you should, watch them, and how you should, or how a different way to pay attention to them. Okay, I can see that in this surface, if we look down this surface, and you can see how viewing is critical. If we look at that surface and I non-proportionally scale this up, we do a pretty clean job of going down here, and then it goes up, but then all of a sudden these CVs are in a weird spot to me. How do they go downhill so much? Or down in screen so much? If we pick those, and I'm going to go back to normal viewing, and we look, it's the curvature row. Well, why does that curvature row, if we now stretch it out in this view, if these are so flat, why does this need to go down so far? You would think this surface would have a negative right here, forcing this to go down, but that's not the case. The reason for this is how these fillets and their interior are constructed. If we eliminate this fillet, or just template it, and we extend radially from this fillet edge, well, right before that, let me point out one extra thing. What I would like to do also, and others may agree, is that I've got a little bit of a strange shape in my tangent line. While this is a good fillet because it's constant, I might want to try to smooth that out a little bit using Chordal, and maybe that's why my center looks weird. So to see what my chord value is, to achieve this minimum section, I need to have the maximum distance between these tangent lines as it's defined right here. So to measure that, I'll switch temporarily to single surface. Now I can measure between two curves, this fillet edge and the adjacent, and we can see that our maximum distance is 4.8425. I will query edit this surface, switch to chordal value, chord length, which is the measurement straight across, and I'm going to set that to 4.85, update, and I'll switch back to multiple. Okay, so now we have this arrangement. We've kind of smoothed this out a little bit, but we still have our downhill or CVs going down issue. Okay? Now let's go back to what I was going to say. If we look at a linear extension, so if we were able to take this surface and extend them straight in that direction, we would get this result. Okay? And it looks pretty flat in this view. If we were to take this same edge and extend it radial or perpendicular to this edge, we would get this result. And if we look at this result from the end view, you can already see that these control vertices start to point down. Okay, and if we use some non-proportional scaling of our view, we have this effect, flat to down. If we go to linear, they all stay flat. This is the proof of why we need flow control on the interior of a surface. Okay, and now I'll show you how I would create this using flow control. And we have to kind of do it manually at this point. So what I need to do is, and I'll switch back to regular viewing, I'm just going to go here to my edge planes that I've defined. If we look at some random colors here, just to show you the surfaces I have on the screen, here's my fillet, exactly the same as what we had, 4.85 edge alignments. But if I want this edge of this fillet to flow perfectly into this edge, I can create that by creating a surface that's normal to this, and then I'll simply extend it. And that will give me where this surface needs to end. That will give me its shape. Okay? Now, how can I tell where the other point needs to be? Well, as we saw in my first example, or in my first iteration, when I did edge control alignment in here to flow or edge align, it really changed this shape. So we know that we need to keep this shape, rather than making it go zigzag, we need it to be flat. So to this point right here, I want to maintain this surface. Okay? So how did I do that? Or how did I find out where that was? I used closest point to measure from there to this surface. It's 1.77. So all I did is offset that surface 1.77, and that's going to give me that exact intersection point and this exact intersection point. Okay. From there, and I'll speed ahead just a touch, I trim these surfaces back. They're still the originals, but I've just trimmed them back to those flat lines. Okay. All I've done here is trimmed those surfaces back to those slabs, okay? And then I rebuilt on the interior the fillets using edge align at both ends. Chord 4.85, 2 mil min, edge align. Now my next step is going to be, or would be, to put this transitional surface in. So I've got that done here, and I'll untemplate it. And I'll query edit it even to show you that it's just a G2 edge-aligned surface. And if we look now down this edge, okay, so again, viewing is critical because I'm looking at these CVs and how they transition. If we look at this edge, you can see how there's an S in here. Why is that? If I go back to my original edge planes, my surfaces sat like this. Okay, so we had a nice clean surface right here. All right, no zigzag. So how did we get this query edit? How did we get this in the wrong place? That's just some tiny mathematical errors in the chord fillet tool, okay, and where it puts that point. So let's measure that really quick, just 0.01, 0.01 of a millimeter, okay? What am I going to do to fix that? Well, one thing I'm going to do is I'm simply going to snap this point on this fillet to this edge. And once we do that, you'll have this surface, okay? Every other point is in the same place, okay? We just moved this point over. And then I put the same, right? It's the same blend. And now we can see what the transition looks like using the correct tangent line. Okay? Got a little issue here where we've actually got too much shape in this set of CVs. It's making this arced. And as we move over, this is a little off, and keep moving over. This is off, right? Look up this edge. We've got a little issue here. All right. Go up here. Little issue here. Go up to the top. Potentially a little issue here, right? It'd be nice if these were all really smooth. Again, we're talking minute differences here. Okay, very small things that if you want these surfaces to be perfect, you need to pay attention at this scale. So my step 6 would be, once I've got these blends made, is just to tweak a few CVs. So I'm going to pick these and just show you how by tweaking a couple of control vertices, so by tweaking these two to those locations, I can get a nice arc right there. Okay, move over here, the same here. All right, move over to here, same here. A nice arc, all right? So that's what I would go to next. You might be asking, well, what's a deviation in there between those two surfaces that you're asking me to change? Let's check the deviation between this surface and this surface. It's 0.002. Very tiny. But when you're measuring at these curvature scales and for the highlights that people are asking for and the min radius requirements, all of these tiny things matter. And I can't stress enough how in the community of Class A users, this stuff matters. All right. So from step number 6 to step number 7, all I've done is shown that at step number 6, okay, so at the point where I've began to modify with hand CV control movements to try to achieve continuity here, I'm still unable to achieve continuity right here, okay? And I can tell you it's at a very minute level. And when we get values that go up by 1, if you remember, that means we almost don't need to pay attention. But to achieve this continuity in the end, I had to modify this surface. This surface had to be more continuous in this area to allow continuity across here and here. So that solution is right there. And now we've got curvature on all boundaries, okay? And now the last thing I would like to show here is last minimum radius check. So if I grab this profile, just grab these guys in here. Like we got 2 maybe. If we grab these and we ask it for curvature, we're way over our curvature, right? We've got 2.5, 2.6. So in all of our work, right, it appears that we've lost achieving our minimum. So we've kind of got a fatter radius, almost by a millimeter in certain areas. So that doesn't seem good. But take note, the curvature combs are measured in the U and V space of the surface, not radially. And radially is the only way to truly measure a fillet's min radius. So a good tool to use to measure min radius, I've got it on my palette, is eval check min radius. All right. So if I go to check my min radius, all right, I've got principal max set to 2.05. I could set that to 2.0, and it's checking for min radius. Now this is saying that's the minimum radius, is over here. Okay, and it doesn't pass 2.0. Well, you could say, well, why does this say 2.85? Well, one is measuring radial to this line. The other is measuring along the U of this surface. And that's not an accurate measurement for minimum radius, because where that says minimum radius is 2.85, the actual 3D min radius or minimum radius value, and I've got a slight issue here. I've got an extra surface. Query Edit allows you to pick on here. My min radius right here is actually 1.97, 1.96. Okay, so that value right there is off. Actually, it's not off, it's just not reading the minimum as cut through their true radial and 3D. Okay, and then you can raise this number up to, let's say, 2.1. Okay, so I'm right at 2.0 or 2.1 almost all the way through there. Okay, so that type of blending can be used. In this case, we used it on a very small blend, but that kind of blending and transition, so flow control, can be used on all sizes and forms of radii, and it's a very important topic that we'll keep discussing.